In today's lesson, we are going to be verifying properties of triangles and quadrilaterals. So we're just going to be taking, again, the same concepts that we've looked at previously, the midpoint, length of a line segment, slope formulas, and use that to help us verify certain properties or just verify if a certain shape is a quadrilateral or a type of quadrilateral or a certain type of triangle. So this table is just kind of looking or going over the different types of triangles that we may come across, such as a scalene triangle, isosceles, equilateral, and so on. And it does tell us kind of what we're looking for. Right? So if we're looking for a scalene triangle, we want to find the lengths of all sides. Right? We want to prove that all the sides are different lengths. Isosceles, again, we're looking for two sides that are the same, so we have to find the side or the lengths of all sides, and hopefully two of them work out. Equilateral, right? All three sides are equal, so again, we're trying to find the side lengths. Right angle triangle, we've done an example of this already, right? We do need to look for that 90-degree angle. Opposite sides are parallel. Right? So opposite sides are parallel. We have to find the slopes of all the sides and check to see that the opposite sides are parallel. This is going to require some drawing just to kind of get a general idea of where the points are in relation to each other, so we can look for what side we're looking for and so on. Rectangle, parallelogram with which all angles are 90 degrees. So we should be looking for 90-degree angles. We can also find the side length or the length of all sides. Show opposite sides have the same length and show that the adjacent sides, the slopes are negative reciprocals. Right? So we're looking for two things here: that the opposite sides are equal in length and that the adjacent sides are negative reciprocals, meaning they meet at 90 degrees. Square, right? All sides are equal, so looking for all sides, we do have to double check to make sure that the angles are 90 degrees. We do need to find slopes. We only really need to prove that there's one 90-degree angle. If all the sides are the same, we have one 90-degree angle, the rest has to work. Because if not, all sides are equal and there's not a 90-degree angle, then we have what is called a rhombus. So a rhombus, all sides are equal, but there is no 90 degrees. Right? So we want to find the length of all the sides, and if all sides are equal, it is a rhombus. Now, a square is a special type of rhombus, so we could classify everything as a rhombus. If we want to check to see is it a square, we have to look for that slope. So, first example is show the quadrilateral EFGH with vertices E -5, 4, F 2, 8, or -2, 8, G 6, 2, and H 3, -2 is a rectangle. So we're being told that it's a rectangle. So let's go through. I'm going to just quickly draw my shape in here. Let's go through and roughly label where these points should be. Right, so if I'm looking at them, we have, and this is not going to be 100% accurate as long as we're relatively this idea. So we're going to do G is 6 and 2. We're going to have H, which is 3 and -2. I'm going to remove this rectangle just because it is going to maybe get a little bit confusing. I'm just going to plot these points roughly where I think they should be. So we have E, which is -5, 4. So F, which is -2, 8. Be up here. I'll bring this down a bit. G, which is 6 and 2. 6 and 2. And 8, which is 3 and -2. Now, the only reason I'm drawing this is just for reference to know which points make up which sides. Right? So again, do not trust drawing or the accuracy of this, right? Because based off this accuracy, obviously it's not a rectangle. Right? But I'm just doing this to roughly see where the points are in relation to each other. So when I'm calculating a side length or slope, I know what to look for, I know which points to use. So the first thing we want to do, if it's a rectangle, we want to first check or find the side lengths. And what we should find is that the opposite sides are equal. So EF should be equal to HG, and AFG should be equal to EH. Again, we are going to use our length of a line segment formula. So that was the distance is equal to the square root of x2 minus x1 squared plus y2 minus y1 squared. So the first one we're going to do is we are going to do EF. So side length of EF is going to equal the square root of I'm going to have f my second point. So the second letter is going to represent the second point. So we have -2 minus -5 squared plus 8 minus 4 squared. Length is equal to the square root of 3, or so it's 3 squared plus 4 squared. I get 9 plus 16, or the square root of 25, which gives me a length of 5. So I have side EF. Actually, I'll leave that there. EF. We're going to go through and we're going to find next HG, just to make sure that these two are the same. So we're going to do HG in same formula. G is going to be my second point. So we're going to have 6 minus 3 squared plus 2 minus -2 squared. We have 3 squared plus 4 squared. And right from here, I don't even need to go any further because I can tell that this is going to be the square root of 25. I'll go through it anyways, and I get 5. So I know that EF and HG are equal. So that is a good sign. So I'm going to put a line there between each to recognize that they are the same. We still have to go through and double check the other ones. So FG. So F is my first. So we have 6 minus -2 squared plus 2 minus 8 squared. We have 8 squared plus -6 squared. FG is equal to 64 plus 36, so square root of 100. And get FG is 10. And that doesn't mean anything right now, right? That's just the length. I do need to double check that EH, this one here, is also the same. So EH should work out to 10. So we have 3 minus -5 squared. Plus -2 minus 4 squared. We get 8 squared plus -6 squared. And okay, I get the same answers or same values as before. So when I go through, square root of 100, EH is equal to 10. So that's good. So we've proven that the opposite side lengths are equal, which is a good start. Now what we need to do is we need to double check that we have a right angle, right? So we do need to find our slopes. Now, we only need to really find that we have an adjacent pair of slopes, or a pair of adjacent sides or meet at 90 degrees or are negative reciprocals. So we're going to check the slopes as our second step. And we are going to look at EH and HG. So the purple and the green line. So we're going to check first. We're going to use, we'll use both methods. We'll use our table of values for the first one. So we have X and Y. For EH, we have -5, 4, and 3, -2. Change in Y, we have 4 to -2. That is a negative change of -6. We have change in X from -3 to 5. That is a change of 8. So then the slope of EH is equal to -6 over 8, or we could say -3 over 4. So that's the first one. I'll do the second one for HG as in the algebraic formula. So the slope of HG is going to equal y2 minus y1 divided by x2 minus x1. So we get 6 minus 3 divided by, that's the x value, sorry. We get 2 minus negative 2 divided by 6 minus 3. We get 4 over 3. And this means that therefore the slope of EH is perpendicular to the slope of HG. So then therefore EFGH is a rectangle. So we've proven that the opposite sides are the same or are equal, and we've proven that the two sides or two adjacent sides meet at 90 degrees, meaning that all the other ones would have to meet at 90 degrees as well. So it's just, again, about using the slope, midpoint, length of a line formulas to kind of prove some of these statements. Now, we didn't use midpoint in this case, which is fine, right? But we did use length of a line, we did use slope. Given points A, B, and C, A being negative 1, 3, B being 1, 7, and C being 5, 5, we want to verify that it is a right angle triangle and then determine whether or not it is isosceles. So the first thing we need to do is I'm going to label or plot our points. So we're going to plot our points. Again, I'm just going to roughly plot where they should go. So negative 1 and 3, we'll say is here. B is 1 and 7, so up here. Maybe a little closer here. And C is 5, 5, so somewhere about here. So I'm just going to roughly draw my lines. And the reason we want to do this, again, not to accurately check to see if it is a right angle or an isosceles or not, we want to just double check or know where the points are in reference to each other. So the first thing we got to do for A, if we're determining if it's a right angle or not, we have to find the slopes. I'm going to leave it, we're going to keep using the algebraic formula because I do want to try to get comfortable using that rather than creating a table. If you feel like you still need to create a table, that you're more than welcome to. I'm just going to focus on the algebraic formula. So looking at this graph, this diagram, I'm assuming if my points are roughly plotted where they should be, I'm making the assumption that my right angle should probably be here. If I were to have one, it should be here, between AB and BC. And this helps give me an idea of what lines I should be checking the slope for. If you're not sure which one to check them all, find the slope of each line segment, and check to see if any of them are negative reciprocals. So first one, we are going to do, I'm just going to work through these two. So the slope of AB is going to equal y2 minus y1. So we have 7 minus 3 divided by 1 minus negative 1. We get 4 over 2, or 2. I'm going to check the slope of the other line of BC. So m of BC is equal to y2, which is 5 minus 7 divided by 5 minus 1. I get negative 2 divided by 4, or negative 1 over 2. So looking at these two slopes, therefore, the slope of AB is perpendicular to the slope of BC. So therefore, it is a right triangle. So we've proven that it's a right triangle. The next step is to determine whether or not it is isosceles. So we do need to check to see if we have any two of the same line or same lengths. So for B, we're going to find side lengths. Again, we have the formula. The distance or the length is equal to x2 minus x1 squared plus y2 minus y1 squared, and then all square rooted. So I'm just going to go through and find each one. Now, I'm going to find each one just because my graph is roughly drawn. It's not accurately sketched, so I don't know if those side lengths are in appropriate dimensions. So we're going to find the length of AB. So the square root of, we have 7 minus 3 squared plus 7 minus 3 is the y's. So we have 1 minus negative 1 squared plus 7 minus 3 squared. And if you think about it, we could take the rise and run, the two values from what we just found, and square those, because we do get the same thing. So we get 2 squared plus 4 squared. Or 16 plus 4, which is the square root of 20. Now I'm going to leave it at that. I don't really care about the decimal, because if I check my other answers and I get the square root of 20, then I'll know that they'll be the same length. So just saving myself a step or two. I'm going to check BC next. We're going to go through and do the same thing. So x2 minus x1, so we have 5 minus 1 squared plus 5 minus 7 squared, all under the square root. We get square root of 4 squared plus negative 2 squared. 16 plus 4, we get the square root of 20. So B and C are the same length, or sorry, BC and AB are the same length. However, we still need to find the other length, because if the other length is also square root of 20, then we have an equilateral triangle. So we do still need to go through and check, even though we found that two sides are the same. So the length of this last step or last point is going to determine what type of triangle it is. So we have 5 minus negative 1 plus 5 minus 3. We get 6 squared plus 2 squared. 36 plus 4, we get the square root of 40. So just by looking at that, we can say, okay, this is not an isosceles triangle. It is not an equilateral triangle, because two sides are the same. So therefore, it is isosceles because AB is equal to BC. Right? Two sides are the same. So we've proven that statement, or those statements, where we verified the type of triangle. The last one, we want to determine the type of quadrilateral defined by the following vertices. So this one's going to be a little bit more time consuming just because of the type. It's very vague, and we have many different quadrilaterals that it could be. But in any case, the first step should be plotting your points to roughly see where they fall. So let's see, we have 2 and 3 for A, 2 and 3. B is 5 and negative 1. C is 10 and negative 1. C, and D is 7 and 3. So between there. So we might already be able to kind of tell what type of quadrilateral is going to be, or at least narrow it down based off of these dimensions, right? We probably can tell by looking at, okay, it's probably not going to be a square or a rectangle, but let's double check anyways and go through right? Maybe it's a parallelogram or a rhombus or something like that, but we can probably exclude square and rectangle. So the first thing we're going to do, the first step, right? We want to find the side lengths. We're going to find the side lengths for each side. So we'll start with A, or it doesn't really matter which one we do. We'll do AB. Why not? We'll just keep it kind of alphabetical. So AB. And we'll put out the formula again just in case we forget. x2 minus x1 squared plus y2 minus y1 squared. AB. And then all under square root. Keep forgetting to say that, but hopefully we are comfortable with the length of a line segment formula since we've been using it so often. So AB, we have 5 minus 2 squared plus negative 1 minus 3 squared, all square rooted. We get 3 squared plus negative 4 squared. We get the square root of 25 or 5. If we're just comparing or checking, we can probably just leave it as the square root or the root value. We don't really need to go through and evaluate that because as long as we get the square root of 25 elsewhere, that's enough. So the next point, we'll do BC. So again, same idea, BC is equal to the same formula. We'll start with C, so 10 minus 5 squared plus negative 1 minus negative 1 squared. We get 5 squared plus 0, because negative 1 minus negative 1, negative 1 plus 1, so we're at 0. 5 squared is 25, which equals 5. Okay, so we're in a promising step, right? All the first two sides are the same, but let's go through because we do need to prove and verify. We don't want to have any missing pieces. So we'll do C and D. So the length of CD, we have 7 minus 10 squared plus 3 minus negative 1 squared. We get negative 3 squared plus 4 squared, so 9 plus 16 equals the square root of 25, which equals 5. So far, all three of these sides are the same. There's a good chance of what the next one is going to be. But let's go through and just verify so we can prove that anyways. So the last one, DA, we have 2 minus 7 squared plus 3 minus 3 squared. We get negative 5 squared plus 0 squared, or 25, which is 5. So we've just proven that all sides are the same. So now that leaves us to two options, right? This is going to be either a rhombus or a square. So the difference, or what we need to do now, the last step, is because it could be either one of those two, we need to determine what are the slopes, right? Do we have perpendicular lines? So this next step is we have to find the slopes. And we really only have to do one, right? We only have to do one pair of adjacent sides. If they're the same, or if they're the negative reciprocals, then it is not a rhombus. Or yeah, it's not a rhombus, right? So if the lines are perpendicular, negative reciprocal slopes meet at 90 degrees, then it is a square. If they are not negative reciprocals, then it will have to be a rhombus. We only have to really do one calculation, or two slope calculations. Again, like I said, we're going to stick with the algebraic method, y2 minus y1, y2 twice, divided by x2 minus x1, We're going to do AB first. So AB is equal to negative 1 minus 3 divided by 5 minus 2. We get, not AB, it's the slope of AB. Then we get negative 4 over 3. And for the next one, the slope of BC, we have negative 1 minus negative 1 over 10 minus 5. We end up with 0 over 5 or 0. So because these slopes aren't negative reciprocals, they're not even the same, we can confidently say that therefore all sides are equal with no right angles. So it is a rhombus. So it meets those characteristics of a rhombus. All sides are the same. We don't have any right angles. We don't really care what the angles are in this case, as long as we know that they're not right angles. So from this lesson, a lot of it was just going through and just verifying or looking at the different properties or determining what type of triangle or quadrilateral it is, using the concepts that we've previously looked at: length, side length, or same thing, midpoints, slope. We didn't really use any midpoints in this case, but we have looked at applying midpoint formulas in previous lessons, so that may be something that you do have to do. But again, we're getting comfortable using those formulas and using that to verify certain properties. So again, make sure you're comfortable with those formulas, because that's where everything starts. Right? So make sure you can find the side length, calculate slope, midpoints if necessary, to help prove these properties.